Hi guys, this is the continuation of the video for 4.7, which is the last section that's going to be on your exam next week. If you guys remember, this was L'Hopital's rule that we were talking about. So we had kind of returned to the topic of limits. And today we have kind of a tricky technical topic we're supposed to cover. So I wanted to go over it just so you guys are prepared for online homeworks. But I will, of course, be posting a exam review video before the exam next week. So if it's on the exam, you guys can kind of prepare yourself for a problem like this. So these are called indeterminate forms. And something that has an indeterminate form was like 0 over 0 and infinity over infinity, which we've been working with. But there are some more indeterminate forms. For example, 0 to the 0 power, 1 to the infinity, and infinity to the 0 power. So these are just terms that they could equal different things depending on where you're approaching the limit from. So we have a way to deal with something like this. So I guess this would kind of be cheat sheet information, again, only if we end up doing this on the exam, which I don't know yet. So this is how to deal with indeterminate forms. So basically this is if you're taking a limit and you end up getting one of these guys, so the 0 to the 0 power, 1 to the infinite power, or infinity to the 0 power, which it's just a method on how to deal with it, just like we had methods to deal with 0 over 0 and infinity over infinity. Now we're talking about these guys. So step 1 is to represent the function that you're taking the limit of as f of x to the g of x. This will make more sense when we do an example. Step 2 is to evaluate L, which is equal to the limit as x goes to some alpha. These forms are what you're getting by plugging in alpha for us taking a limit as x goes to alpha of some function f of x. Okay, so we evaluate our limit as x goes to alpha of g of x, where g of x is our exponent here, times the natural log of f of x, where f of x is our base term here. And then we have 3 possible step 3s, depending on what we get. So first of all, if L is finite, so if this limit up here is finite or not equal to infinity, then the limit as x approaches alpha of f of x to the g of x, which is just our original function we're trying to take the limit of, is equal to e to the L, so e to whatever you got for this guy. If L is infinity, then the limit as x approaches alpha of f of x to the g of x is equal to infinity. And if L is negative infinity, then the limit as x approaches alpha of f of x to the g of x is equal to 0. So this is kind of a convoluted process, so we're going to do some examples and hopefully that'll make a lot more sense. And then we're done with this section and we'll move on to section 4.9 tomorrow. I know tomorrow we don't normally have class, so don't really worry about it. Again, 4.7 is all that'll be covered on the exam next week. So this is mainly what you guys need to worry about. All right, so example 1. We're going to find the limit as x approaches 0 from the positive side of x to the x. So if we just plug in, we're going to get 0 to the 0, which is indeterminate. So we're going to use the process above. So from step 1 up here told us to represent our function as f of x to the g of x. So we have our function is x to the x. So both f of x and g of x are equal to x. So we'll just write that down. F of x is equal to x, and g of x is equal to x. Step 2. Step 2 says to evaluate this limit. And if we write that out, it's the limit as x approaches alpha, where alpha is just whatever we were originally taking our limit of in the first place. And we have the limit as x approaches 0 from the positive side of g of x, which we know is just x, times the natural log of f of x, which again is just x. So if we plug this in, sorry guys, I got lost in my own notes. If we plug this in, the natural log of 0 isn't really defined. It's negative infinity, and then times 0 doesn't really make a lot of sense, so we're going to have to use L'Hopital's rule. So we could rewrite this. This is actually kind of a neat trick that you guys might find helpful on homeworks. We can leave the natural log of x in the top, because remember, we can't use L'Hopital's rule unless we have a function divided by another function, but we can kind of fake like we're dividing, because if we divide by a fraction, it's the same as multiplying by reciprocal. So we just need to find the reciprocal of this guy and divide by it. And the reciprocal of x is just 1 over x. So hopefully you guys can agree with me that x times the natural log of x is the same as the natural log of x divided by 1 over x. And now we can use L'Hopital's rule because we have a fraction. So we know that this is equal to the limit as x approaches 0 from the positive side of the derivative of the top. So the derivative of the natural log of x is 1 over x. Let me just write a note that we're doing L'Hopital. Divided by the derivative of the denominator is negative 1 over x squared. And if we rewrite that, we get the limit as x approaches 0 from the positive side of negative x squared over x. And this is equal to the limit as x goes to 0 from the positive side of negative x, which is just 0, because negative 0 doesn't really make a difference. Okay, so we're not done. We still have another step. So step 3, we have that L is equal to 0, which is finite, right? Because finite just means not infinity, or positive or negative infinity. Oops. So the limit, our original limit, as x goes to 0 from the positive side of x to the x, if we look at our kind of cheat sheet steps, it says that this guy is going to be equal to e to the L, and we have the L as 0. So this is equal to e to the 0, and e to the 0 is just 1. So that would be our final answer. Okay, let's do another step, or another example, just to reaffirm this process in your guys' minds. So example 2, we're going to find the limit as x approaches infinity of 1 plus 1 over x to the x. If we just plug in, we'll get 1 to the infinity, which is one of our indeterminate forms. Also, as a side note, I just wanted you guys to know that yellow is definitely not going to work. Okay, let me do a side note up here. 0 to the infinity is not indeterminate. It's just 0. Because if you have any 0 times whatever number, it's going to be 0. The reason that like 1 to the infinite is not necessarily 1 is because you could have 1 be a fraction, and any fraction, like before we reach 1 as our limit, we could reach infinity sooner. And if we reach infinity sooner than this gets to 1, then this guy's a fraction, and a fraction to the infinity is actually 0. So that's where these indeterminate forms come from, but 0 to the infinity is not indeterminate. Okay. So anyway, for the problem that we're working on right now, we know we have an indeterminate form, so we're going to go through our steps for dealing with this. Step 1 says to represent it as f of x and g of x, so f of x is our base here, which is just 1 plus 1 over x, and g of x is our exponent, which is x. Okay, step 2 is where we evaluate L, that limit. So our limit is the limit as x approaches infinity, because we just use whatever limit was in our original problem. And then remember, it's the limit, if you look up here, it's the limit of g of x times the natural log of f of x. So we have the limit of g of x, which is x, times the natural log of 1 plus 1 over x. Okay, so once again, if we were just to plug this in right away, we would get an infinity here, because plugging in infinity for x is just infinity. And then plugging in an infinity here gives us a 1 over infinity is 0, so this would be 1 plus 0, which is just 1. And the natural log of 1 is negative infinity, so 0. And so that would be infinity times 0, which is not something we have defined. So again, we're going to use kind of that L'Hopital's rule trick by noting that multiplying by x is the same as dividing by 1 over x. So we have this is equal to the limit as x goes to infinity of the natural log of 1 plus 1 over x divided by 1 over x. Okay, so now we're going to use L'Hopital's rule. And we have the limit as x goes to infinity. We're going to take the derivative of the top. So the derivative of the natural log is 1 over what's ever on the inside, and we have 1 plus 1 over x. And then we need to multiply by the chain, and the chain is negative 1 over x squared, because that's the derivative of 1 plus 1 over x. The derivative of 1 is 0, and the derivative of 1 over x is this negative 1 over x squared. Okay, so that's our numerator, and then we divide by the denominator's derivative, and the denominator's derivative is just 1 over, or negative 1 over x squared. So these guys cancel, and we get that this is equal to the limit as x goes to infinity of 1 over 1 plus 1 over x, which is just the limit, or sorry, once we plug this in, we don't need to write limit anymore. The limit as x goes to infinity of 1 is just 1, and then the limit as x goes to infinity of 1 plus 1 over x is 1 plus 0, which again is just 1, so our limit is 1. Remember, we're not done yet. We have 3 steps to this process. Sorry. So for step 3, we have L is equal to 1, which is finite. So our original limit that we're trying to take, so limit as x goes to infinity of 1 plus 1 over x to the x, is equal to e to the 1, which is just e. And this is actually something that if you're going on to Calc 2, you will actually be using a lot. This fact that the limit as x goes to infinity of this particular function is equal to e. And actually, just like a quick side note for those of you who are interested, if you're not audios. But it actually happens that, as a rule, if you can have the limit as x goes to infinity of 1 plus 1 over x to the x, is actually, we can replace this 1 on top here with any number, and it's going to be e to that number. And there's a way to prove that. We don't have to go through that. And technically, these don't even have to be just x's. This could be 3x and 3x as long as they match. So, for example, and this again is just like bonus material, especially if you're moving on to Calc 2. So if I have the limit as x goes to infinity of 1 plus 2 over 3x to the 3x, because these 3x's match, that's just going to be equal to e squared. Again, that's something you will be using in Calc 2 if you move on, and I just think it's kind of interesting. But being able to do this is what we're focused on in Calc 1. Alright guys, so that's the end of section 4.7. Our next one will be 4.9. But once again, this is the end of the material for exam 3. So if that's all you're focused on, there you go. Alright.